Well, hello and welcome once again to Doc Ontco Physics. My name is Keith Ontco, and today what we're going to be doing is taking a look at how to solve vectors in a graphical method. The way that we normally do it in physics when we want more accuracy is we do it with algebra, but one of the first ways we learn to analyze vectors is simply by putting them on a piece of paper and manipulating them graphically to see just what happens to a vector. So let me start out, if you haven't seen one of the other videos, is to talking about just what a vector is. Well, a vector is something that has not just one component, but it has two components. Right? If you think of a scalar is a type of number. In fact, a scalar is a number. And if I wanted to say that I have 12 cookies, or 10 nails, or 8 pens, right? The numeric part of that, the 8 pens, or the 12 cookies, or the 10 nails, the numeric part of that is the scalar piece. Okay? But when we solve problems in physics, oftentimes we need multiple characteristics about a certain measurement. Okay? If, for instance, I lived, let's see here, well, I can't do it on the screen quite yet. Let's say that I lived 2 miles away from you, and I told you, hey, why don't you come on over to my house this afternoon, just walk 2 miles. Well, that would be a problem because I didn't give you a direction, right? You could walk 2 miles and you could get really lucky and you could get to my house, or you could walk 2 miles in some other direction and you could be 2 miles further away, 1.5 miles further away. You could be anywhere within a certain radius, right? And so when we want to describe something that has both a magnitude, a number part, and a direction, we use something called vectors, okay? And what I've done is over on the right-hand side of the screen here is I have drawn some vectors, okay? Let's see here. And I've given them different colors. I've got a red one up here, I've got a blue one here, a green one here, and a black one here. And notice that they are different lengths, and they are all going in different directions, okay? And so, and I've drawn also a coordinate system, right? And it's always helpful in physics to draw a coordinate system before we really do any kind of problem that we do, vectors being one of them. So if I want to add vectors together, okay, the best way that I can add them, the only way that I can add them, right, graphically anyway, is I have to add them tip to tail, okay? And that's very important, right? The tip is this portion up here. It's the portion with the arrow. The tail is the portion without the arrow, all right? So it's that easy. I can only add together a tip up here to another tail. So it's called the tip to tail analysis method. So let's say that I would like to add these vectors together, all right, and get some resultant vector. So I'm going to take my first vector here, and I could take any of these, right, and use them as my starting vector. It makes absolutely no difference the order in which we add vectors together graphically or algebraically. It makes absolutely no difference. You'll get the same answer each and every time, and I'll show you that in a minute. Okay, so I chose the red one first. I'm going to choose the black vector here next, and I'm going to slide this up here. And notice that I am free to move vectors around on my paper here as long as I do not change either the length of the vector or the direction of the vector. Okay, so that's all I'm really doing here, is I'm simply moving them around on my coordinate system. I started at the center, right, and I add tip to tail, right? The tip of the arrow here to the tail of the arrow on the next vector. And so now let's take the green one, and I'll move the green one up here. Okay, if I can do that, there we go. All right, and then finally, I'll move the blue one. And again, note that I've added all these things tip to tail, all right? So the tail starts out at the origin of my coordinate system, right? And here's the tip of the arrow, right? The tail of the next vector, the black one, right, is attached to the tip of the first one, right? The tip of the black arrow gets attached to the tail of the green arrow, and the tip of the green vector gets attached to the tail of the blue arrow or vector, if you will. So now what I've done is I've added all these things together, but what this creates is something called a resultant vector. So what I'm going to do is I'm going to add in a resultant vector here. I'm going to choose from my shapes an arrow, and the resultant vector will always start at the origin, right here, right? Whoops. Starts at the origin, and it will end up at the final location of my, whoops, it got moved there, of the final arrow, or the final vector. This is not working out as smoothly as I would have liked. There we go, right there. And I'm going to give this guy a different color here. Okay, so what I've done is I've changed my resultant vector to a brown dashed line. Okay, so this is my resultant vector right there. This is what I'm looking for. So in essence, I could have gotten from the origin right here all the way to this final vector right here, right, the final blue vector, either by following the red vector path and the black vector path, the green vector path, the blue vector path, right? I could have followed those vectors and I could have gotten to my final destination, which would be down here. Or I could simply have followed the brown dashed vector, right, and gotten to my final destination as well, right? These are what are called equivalent vectors. The four vectors, red, black, green, and blue, when added together vectorially, are the equivalent of the brown dashed line vector. They're the same thing, because when I add them together, right, add red, black, green, and blue together, I get brown. Brown is my resultant vector. Okay. Now, what I want to do is I want to show you. Now, I'm going to move my resultant back up here. Now remember, I'm not changing the length of my resultant, nor did I change the direction of my resultant. Right? I simply slid it over here, and I noted I had red, black, green, and blue. That was my order before. I'm going to change the order in which I add these things together, so that you can see that the order makes absolutely no difference. Whoops, can't move it all the way over there. All right. So I had red, black, blue, and green before. Let's change the order to blue. So I'm going to start the blue one at the origin. All right. So that's there. It's a little hard to see because my grid lines are also blue. My second one's going to be green. Okay, slid that one over there, but notice I'm not changing the length of the vector at all, or the direction of the vector. Next, I think I'll go, let's go red. Okay, so red is going to go right about there. Okay, and then black. And remember, notice that I have added all these things tip to tail, and I've been as careful as I can be here. So I've added these tip to tail. So I have the blue one here, right? And I started with the tail at the end, and I've got the tip here. Tail always starts at the origin. Got the tip here, and then I added the tail of the green one to the tip of the blue one, and the tail of the red one to the tip of the green one, and the tail of the black one to the tip of the red one, and here's my final destination here. Well, I'm going to bet you that if I move my resultant vector that I got from the first one, whoops, come on, and I put it right at the origin, then it should still point to a final destination, the same final destination that I got when I added the vectors the first time around, and lo and behold, it does, right? So my resultant vector, this brown dashed line, is the same as it was the first time around. So adding the vectors together with the order that you add the vectors together makes absolutely no difference. Okay, so let's try another problem. Whoops, okay, so let's slide this down here. There we go. So now what I've got is I've got coordinate system again, and I've got 4 vectors, but notice that these vectors are either purely horizontal or purely vertical. Okay, and again, I want to add these up and see what kind of a resultant vector that I get. Well, let's start with the black one. And again, we have to go tip to tail. The tail always starts at the origin. All right, tip is out here. So black, and now I'm going to add both of the x-coordinate vectors together first. Okay, so black and red. Again, tip to tail over here. I'm going to add this one over here. Again, it's tip to tail. And my green one is tip to tail. And what have I got? Well, I've got something that looks like the coordinates in the x-coordinate here and the y-coordinates over here. These become very useful. So what does my resultant vector look like? Well, let me go over here. My resultant is going to start here, and it's going to go up to there. Okay, so my resultant in this case is that thin blue line. This is my resultant vector. What does this look like? Looks like a right triangle to me. Okay, remember that if I add up vectorially the black, the red, the blue, and the green, if I add these up as vectors, what I'm going to get is the light blue vector, all right, starts at the origin and goes to the final destination. Now keep in mind that my final vector here had its tail at the origin and its tip at the final destination. This is the only time when tip will meet with tip, right? The only time that this will meet, I'll draw a little circle up there. That's a bad circle. There we go, I fixed the circle. So now you can see the contents inside the circle. So this is the only time that tip will meet with tip, and that's when you've drawn in the final resultant vector. Okay, when you're adding vectors, okay, it's always tip to tail, tip to tail, tip to tail, tip to tail. Okay, notice, right, that what I have here is I have 2 x-coordinates, two x components, the black and the red vectors on the x coordinate system, blue and green and the y coordinate system. So what have I done? I've taken and added these x coordinates, right, and then vectorially added y coordinates, and I got a resultant vector. This is a right triangle, right? When we analyze these algebraically, what we do is we take our resultant vector here and we break it down into x coordinates, right, our black and red vector, and y coordinates, our blue and green vector. This becomes very important when we want to analyze physics problems when we have to deal with vectors. So I hope that helped, and I hope that you have a great day.